A warm welcome to all of you. I, Akash Sharma, on behalf of Midas IT, welcome you all to this release webinar for GTS NX version 2017 1.1. So today in this webinar, I'll be talking about the enhancement or developments in the software for this particular version. As you can see, it has been categorized into two major divisions. First one being the analysis portion and the second being the pre and the post processing. So I'll be talking in detail about each of them today in this webinar. So to start with, we'll start with the analysis portion, and the first enhancement is the auto calculation of the K0 and the K0 NC parameters. GTS NX 2017 provides you with the option of automatic calculation of K0 parameter based on the friction angle value for material models like Moore-Coulomb, Drucker-Prager, and hyperbolic material model. Okay. Even for modified Moore-Coulomb, soft soil creep, hardening soil, the K0 NC parameter can be directly determined using the friction angle value. And then if you select the automatic K0 determination, the program will automatically calculate its value based on the K0 NC OCR value, that is the over consolidation ratio, and the Poisson's ratio value. For the generalized S-clay model, one can manually estimate the K0 NC value, and the program again, when selected for the automatic calculation, will calculate the K0 value based on the K0 NC, OCR, and the Poisson's ratio input. Please note that the manual input option is also available if the user wants to use his or her own value. Now, user need to check the option of K0 in the analysis control dialog to activate the stress condition in the model based on the K0 parameter. So one should take care of that. So moving on is the enhancement of the modified UBC SAN model. As you know, that modified UBC SAN is an effective stress model for predicting liquefaction behavior of sand under seismic loading. GTS NX liquefaction model is now extended to a full 3D implementation of modified UBC SAN using implicit function. I will brief you about the function used to consider the various behavior of the material model. For example, for the nonlinear elastic, it considers the exponential function based on the effective pressure. For plasticity or shear, the yield function is as per the Moore-Coulomb criteria. In the plasticity and shear, the non-associated flow rule is as per the Mentry-Williams theory, and the hyperbolic hardening is considered for the hardening behavior. Compression cap yield function is as per the modified Moore-Coulomb cap. Okay, the flow is associated with as yield function defined considering as associated flow, and the hardening of allowable compression per volumetric strain is considered. Yield function and the flow rule is taken as per given equation for the pressure cutoff. Now, while considering the cyclic behavior, taking consideration of shear, plasticity function for primary and secondary yield surfaces are important, and the difference is checked for the hardening behavior. Primary yield function is a state when the current stress ratio reaches to the critical or the maximum state of the material. Secondary is a state where still the maximum state of the material is not reached according the loading and unloading conditions. And based on this state, the hardening is considered. The secondary densification the secondary hardening or the soil densification is considered based on the F dense input in the material definition. When the maximum stress ratio is reached or the mobilized friction angle reach peak value of, and then the liquefaction is triggered. Okay. So this was about the modified UBC SAN model enhancement. Now let us talk about the input parameter required for this particular material model. Now to simulate the liquefaction, one need to define additional parameters for this material model. To use the model, one can use the SPT test blow count for clean sand to get the desired inputs and hence make it desirable as a material model, because all of you know that the SPT values are easily available. Highlighted are the equation to get the input for the UBC sand models using the N count value. Elastic shear modulus number and the plastic shear modulus number can be directly taken from the N60 count. Even to determine the peak friction angle based on count being greater or smaller than 15, correlation exists. This correlation helps to use the advanced model like modified UBC sand with much ease. Now in the advancement for the modified UBC sand, we have in the pre and post processing part the liquefiable area. Okay, so with liquefaction, now the model GTS NX gives two specific results, which is the pore pressure ratio and the normal maximum shear ratio. Pore pressure ratio is the ratio of the excessive pore pressure change and the initial effective pressure. By literature, as you know, that when we get the value of PPR as 1, one can conclude that the liquefaction is triggered in that particular model. Now second is the normalized maximum stress ratio, which is the ratio of the mobilized friction angle and the peak friction angle. As discussed, when it reaches the value of 1, we have the layer or soil liquefied. Now with this feature in the post-processing part, one can now avoid extracting the results and taking to Excel to check the status for the liquefaction. You can directly come to the post-processing now and check what is the condition or which area is liquefied or which areas are prone to get liquefied directly. Okay, now modified UBC sand results model calibration. Now the validation of the model is done by comparing skeleton response to the material model for monotonic and cyclic drain DSS test, which is the direct simple shear test, With constant volume, one can go for undrained simple shear test. Now shown are the graphs for the validation of results as obtained from GTS NX UBC sand material model and the laboratory test. Soil densification can be considered very much similar to what we obtained in the soil lab test in the shear stress vertical stress plot as shown in the image. Okay. Then a case study on the modified UBC sand. Okay, so as discussed, when maximum possible stress ratio is reached, liquefaction is triggered, and then the plastic shear modulus is reduced as per the user-defined post-liquefaction calibration factor. Considering an embankment resting on UBC sand layer, nonlinear time history analysis was performed under cyclic loading. Highlighted are the results at various time interval, which shows basically the normal maximum stress ratio. So now with the post liquefaction factor, one can even see the normalized maximum stress ratio change in the model even post liquefaction. Okay. Now talking about the other advancement in the post-processing part and the pre-processing part. First, one will be the seepage cutoff element. Okay. Now GTS NX 2017 provides you with the option of seepage cutoff to provide structural waterproofing members. It can be with 1D and 2D elements for 2D and 3D models respectively. Okay. This seepage degree of freedom helps to decide whether a user allows seepage passing through the seepage cutoff element or not. For 2D models, this can be defined for beam and truss elements, while for 3D it is true for the cell elements. Now let me move on to the program to demonstrate you this particular feature. Okay, so what you can see is a simple embankment, and there is this wall which is modeled as a beam element. Okay, I'm going to show you how exactly you can use the seepage cutoff. So now you can go to mesh. In the element you will find a seepage cutoff option. Click on seepage cutoff. Okay, so in the method type you can select from truss element. Okay, select that portion where you don't want or where you want to apply the seepage cutoff. Now in the property, when you define the property, you have to, if you select the seepage flow of degree freedom, this means that you are allowing the seepage to occur through that particular element. You check this and you give the effective thickness of the structural element. And if you uncheck, you are not allowing any seepage to occur through it. So just say OK. And again, OK. Then you can come to the analysis case. I'm just performing a simple steady state analysis on this model and activate the line seepage cutoff. Say OK, and let us perform the analysis. Now, on completing the analysis, let us check for the flow lines. So when you go to seepage flow path, now if I click at any point, you can see that the seepage is not occurring from this particular element when we have used the seepage cutoff element for the definition part. Okay, so even it is now true for the seepage 3D. Okay, now this is a particular model where we have not considered the seepage cutoff element, so you can see the flow lines occurred. The same analysis case, what we did is basically we activated the element for this portion, that is the seepage cutoff element. Now as soon as I change the method, you can see the analysis case basically where I have activated the seepage cutoff element. You can see the change in the flow lines considering no flow through this element or the wall, which is defined as cell element for this particular model. Moving on to the presentation now. So the next advancement is the improvement in the history output control option. Now in the results, user can check for the nodes for the history output for any specific results. It's need to be defined in the history output probe first before you perform the analysis, and also activate this in the output control data. So once the analysis is performed, you can directly see in the history probe graph that what is the variation for that particular node for any results, being it velocity, displacement, or acceleration. Now let me move on to the program to demonstrate you how to use this particular feature incorporated in the latest version of GTS NX 2017. Okay, so moving on to the program, in this particular model, we are applying some dynamic blast load at this particular point, and we want to see the response of a displacement or velocity at this particular node. Okay, so as already mentioned, to use that function before you run the analysis, you have to come to the history output probe. Okay, so in the history output probe, you can select whatever results you are interested in. You can select a node where you want to see the results and give it a name to add it. Okay, so I've already defined, for example, I've selected this node and I want to see as a result of the analysis what is the change in displacement, velocity, and results for the same node. You can define it for as many nodes as possible. Okay, before running the analysis, while defining or while generating the analysis case, you have to come to the analysis control data, and in the history, you have to move everything onto the right hand sides where you want to see the results. Okay, so you have to move everything onto the selected probe column. Once you have done that, you can run the analysis. Okay, and then you how to see the results, let me just show you. So I'm just moving on to the post mode so that I can directly show you results. I've already analyzed this model file. So once you analyze it, now you will go to results, and in the special post you find history. You can go to graph. Okay. So this is the history probe graph, and you see the whatever point you have selected, automatically it comes. You can directly select it and say draw to see the variation with time for the displacement, for the velocity. Okay, so again I can say draw, and for the acceleration for that particular point as a result of time history analysis. So moving on to the presentation now. So moving on to the next enhancement. Next enhancement is basically to calculate the flow quantity using the arbitrary cutting type. Okay, so with this now the user can check the flow quantity passing through any specific location in your model. Previous version of GTS NX, flow quantity was only measurable at nodes where the boundary condition was defined. So now there are in total 3 options to get the flow quantity. Node and cutting type, where user can calculate the flow quantity by calculating the sum of flow rate calculated at the selected nodes. The third is the arbitrary division type, where basically the program calculates the flow rate of element through arbitrary lines and faces. Please note that while using the arbitrary division type, user should select a location within the elements and not the outermost line of the elements. Okay, so let me demonstrate its usage, how exactly it can be used to take the results out. Okay, so this is a very simple model where I have already performed a seepage and steady state seepage analysis. Okay, so now when you go to the seepage, you have the option flow quantity. Okay, so now let me just add a few cases so that I can show you. So when you say add, fine, so this tab comes out. Now in the modes, you can say there are 3 modes. Node mode, cutting mode, and arbitrary type. I will demonstrate each one of them. So let us use for A, node mode. Okay, so I'm selecting few of the nodes to calculate the boundary, and just I say add. Okay, then in the add, I can use the cutting mode, so I can use, or I can define a line. Okay, say add, sorry, I'll just change the name to A cutting mode. Okay, so just say add. And finally, you can use the arbitrary type, okay, where you can just give it a name B, arbitrary type, cutting mode. Here also you can define at line at any particular section and just say add. Now you can select this, and when you say calculate, you will get what is the amount of flow expected from that particular cutting mode, node mode, okay, and even for the arbitrary cutting mode. Say calculate, so you will get what is the flow happening. Okay, so this allows users basically to check the flow quantity passing through any specific location in the model. So moving on to the presentation again. Next is the improvement in the extract results function. Okay, now in the previous version of GTS NX, while using the extract function, so what was happening while we were extracting the results, if you select a few stages, as soon as the user changed the result type, he needs to again select the steps completely, which was a bit time consuming if you were having 100 and 200 steps and you already have selected 50-60 steps. Okay, and which of course reduced the effectiveness. So GTS NX with the new improvement, what it will do is it will keep the selected steps checked on even if the user changes the result type. Okay, so to make it more clear, let me show in detail how exactly it works. So I will just move on to the program now. Okay, so this is a simple tunnel model file with a few stages which I have already analyzed for. So when I say extract now, okay, so I go to extract. So let me just move off here. So for example, I'm interested in TZ. Okay, I select this particular node of my interest, and for example, I don't want few of my stage results. Okay, and I just say table. So when I say table, now you can see that I'm only interested in 5 steps. Okay, so previously on changing this, the user need to again check for all the steps. But what happens now, the program retains the selected stages. So even now when you say table, so you get results for only those selected steps without checking it again. So the program retains your selection even if you change the results. Okay. Now let us move on to the program for the presentation for the next improvement. Okay. So the next is the non-hydrostatic water pressure functions. Basically, in the newer versions, there is improvement in the water level consideration for specified mesh heads. GTS NX now also allow definition of non-hydrostatic water pressure for specified mesh heads in the analysis control. So while defining it, it provides now with the 4 definition condition. First is head, so user can define head to an assigned mesh head with the option to give direct head value or varying head using the general function as we used to do earlier. Fine. In the dry condition can also be defined to remove the water pressure from that particular mesh head. The third condition is the hydrostatic condition. It is to define a pressure value to be applied at the top of an assigned mesh head with the condition defined in the non-hydrostatic water pressure function. The fourth option is the user defined, which allows a user to define pressure at the top and bottom of an assigned mesh head with the condition function again defined in the non-hydrostatic water pressure function. Okay, so let me just move on to the program to show you how exactly it works. Okay, so this is a model file. So let me show you, go to the pre-mode. Okay, so here while defining the head, you can consider the change in the head with the x value or the y value by using the general function. Okay, now here you will find an addition of the non-hydrostatic water pressure where the user can define basically user define to basically define the pressure at the top and bottom of an assigned mesh head. So the conditions or the function will be coming in the non-hydrostatic water pressure. Similarly, if you can also select the hydrostatic water pressure condition, okay, so it is to define a pressure value to be applied at the top of an assigned mesh head. Okay, again the condition will be defined in the non-hydrostatic water pressure. So when you define the analysis case, okay, so in the analysis control, so here you can define the global water level, and for specific mesh head you can come over here, you can select the water level conditions from here being dry or hydrostatic, user define or head. Okay, so you can give it for dry, it will consider no zero pore water pressure in that particular head. You can directly give it a value or consider a function, and similarly you can select user define and hydrostatic pressure. Now the advantage of such kind of modeling comes in a situation like this. For example, we are considering some kind of excavation. Okay, now previously let me show you when we used to define a constant head. Let me just edit it. So for 100 meter for the global water level, but for the left hand mesh sets in the model it's 80 meters. Okay, so whenever we used to run the analysis, what the results we were getting is a discontinued pore water pressure towards the bottom. So as I was saying that, now you can see that there is a discontinued pore water variation towards the end. Okay, you have a different value towards where the excavation is happening and where it is defined as per the global water level definition. Okay, so now with the addition of the new feature, what you can do is while defining the water level for different headsets, mesh sets, I'm sorry. So you can define the non-hydrostatic water condition and define your own user-defined condition, okay, to consider basically such changes. Okay, so with this, what will happen when you run the analysis and when you check for the results? Okay, let me just go to again the pore pressure. So now you can see that there is a continuity in what the pore pressure is showing us the results towards the bottom. So such issues can be now resolved with the addition of the non-hydrostatic water pressure. Now let us move on to the presentation. So the next enhancement is basically the import and export of the nodal results. Now these features allow the import and export of nodal results, forces and moments, and also the prescribed displacement excluding the rotation for nodes with constraint defined or at selected nodes through Midas Gen and Midas Civil. Midas Gen being our structural software for general buildings and general structures, and Midas Civil being the software for bridges. So before that, before you import the results, you have to make sure that you have import the MXT file so that the same node number is maintained in both the softwares. Okay, so first thing is you do is you import the MXT file, and then you can go to Midas Gen and export the nodal results and take it through a text format into Midas GTS NX. Let me demonstrate you how. So this is the Midas Gen. Okay, so from Midas Gen, as you know, you have to export the MXT file now and then import it in GTS NX, create the continuum model over there. After that, you can come to export and you have the option called export nodal results for GTS. You do that. Okay, you select the stage for example the load combination if you any, okay, whatever results you are interested in, being it reaction, if you want all the reaction, just select all and just say okay, and you can save the file it as the reactions, okay, or the nodal forces. I'm just saving it the same name, say yes. Okay, so once you have imported the mxt file, now you can come to GTS NX, say import, and go to import nodal results. Okay, select the exported text file from gen, and you will see that directly the forces are imported for that particular load case. All the forces and the moment has been imported and directly applied at the particular node. Okay, so this will help basically the client to take results out of any combinations and directly apply to check what is the settlement happening as a result of that particular loads and forces in GTS NX. So let us move to the presentation again. So the next and the final feature is basically the link between the Liquefaction CAD software and Midas GTS NX. Now this features allow to transfer the structural model from the software, which is the Liquefaction, into Midas GTS NX. The transfer is carried out through Midas converter. This converter transfers such as the structure model data as elements, material, section, boundaries, and loads. The transfer model can be used in Midas GTS NX for a structured ground coupled analysis considering construction state sequence. After the coupled analysis, the converter allows to transfer the obtained results back into the LIRA software. The transferred results have a format of a subgrid modulus for the plate elements, point springs, and spatial displacement. After performing the analysis in LIRA with the transferred results, the analysis results will be the same as obtained in Midas GTS NX. This allowed to make the structural design in LIRA software with real behavior of ground as obtained from Midas GTS NX. So this is all from the enhancement or the developments for GTS NX version 1.1, 2017 1.1. So I thank you all for joining this webinar. Thank you very much.